Hello everyone, it's Benny, and in this video, we're going to start implementing direct light sources. And I haven't really talked too much about those yet, but think of it like this. There's a whole bunch of different ways you can create light sources. For example, maybe you have a flashlight which shines light sort of in this cone pattern that spreads out or something. Maybe you have a light bulb which sort of just illuminates outwards in an area. Maybe it's something like the sun, which sort of is like giant ray all across this huge area, all equally. So there's a few different ways you can create light. So I'm just going to start implementing light sources so that we can start using the equation that I showed you in the companion video for ambient light, where I showed you how we were going to use the rendering equation. So yeah. And with that, let's go ahead and get started. The first one I'm going to implement is a directional light, and that's kind of like the sun. It shines in one direction all equally, across all distances. So I like to think of directional lights as like this giant, infinitely large square of light that just comes down on your screen. I don't know if that helps you or not, but that's how I like to think of it as. So yeah. Now, but before I actually do too much with that, I'm going to create a structure in our fragment shader called base light, without caps lock. And what base light's going to do is this is just going to be the basic components of light, which for me are going to be vector 3 for color, so the lights can have some color, and a vector. No, I'll just do that for float. A float intensity. I was going to do something clever where you could have different intensities in different directions and such, but I decided it's better just to have a constant intensity. And yeah, there you go. So now that we have that, and the semicolon, because LSL is kind of like C in that all structures end with semicolons. So now that we have our base light, I'm going to create the struct for our directional light. And this is of course going to have a base light. It's going to have a base light called base. So it has all the basic components of light, but being a directional light, it's going to have the addition of, guess what, a direction. So I'm going to have a vector 3 called direction, and there you go. That's basically all I want for my lighting structures. So now for lighting methods. I'm not going to implement too much just yet, but I am going to create just sort of a skeleton so that we can fill it out. I'm going to have a vector 4, so it's going to return a vector 4. It's going to be called calc light. So this is going to calculate the effect of any given light. It's going to take in a base light called base. It's going to take in some vector 3 called direction, because even if it's not a directional light, I need to know what direction the particular ray of light is going in that I'm calculating. And finally, I'm going to have a vector 3 called normal. And the reason for that is, of course, if you remember in our sort of approximation of the rendering equation, we needed to know the normal of whatever surface we had in order to calculate how light will reflect off of it, and that was part of the whole equation thing. So yeah. And I think that's all I have in the method for now. I may end up going back and changing that around a little bit, but, well, I am, of course, but I'm just going to leave it like that for now. So, now that I have a generic method for calculating light, I'm going to have a vec 4 called calc directional light. And this will just sort of be a convenience method, which takes in some directional light, and some vec 3 normal, since the directional light doesn't have a normal data with it. And this is just going to be a convenience method, so it calculates the light for directional light, so I don't need to worry about how specifically do I need to call this method in order to calculate directional light. So it's just going to return calc light with directional light. If I can type, .base, there we go. And it's going to, of course, pass in the directional light .direction, because directional light all shines in a single uniform direction. And finally, I'm just going to pass in whatever normal is passed in. So in this case, it doesn't do much. When we get into other light sources, this is going to do a little bit more. But yeah. And this is pretty much the framework I'm going to work with when I'm creating all my lighting stuff. So at this point, I guess I'll just go ahead and implement the calculate method. And this is pretty much just going to be the approximation I showed you in the video where I talked about the rendering equation. So, with that, I'm going to start with the attenuation calculation. I'm going to create a float, and I'm not going to call this attenuation, I'm going to call it diffuse factor, because this is specifically for a type of lighting called diffuse lighting. That's what our approximation right now is considered. So, I'm just going to call it that instead. And just like there, it's going to be the dot product between the direction, actually, the negative direction, because of the equation. I explained it all there. That's why, that's a big reason why I did it there, so I don't have to spend tons of video time explaining it here. So, yeah, between the opposite of the direction and the normal. And that is pretty much going to be what the attenuation is. So now I'm going to do a check if our diffuse factor, so our attenuation, is greater than 0. So if this is having any effect on our surface at all, then we're going to change something. But first I actually need to create that. I'm going to have a diffuse, not a float, what am I talking about? A vector, actually should we do a vector 4, why not? Vector 4 called diffuse color, so this is going to be the color output from our whole diffuse nonsense. And it's going to start as just a vector 4 of 0, 0, 0, 0. Nothing. Absolutely nothing. And if our light is affecting our surface at all, which is what this check is saying, then we're going to change our diffuse color. We're going to say our diffuse color is, we're going to wrap into a vec 4, our base dot color, so whatever color's there, and 1.0. So whatever that is, times, if you remember from our equation, it's BRDF times attenuation times intensity. So this is pretty much all of the BRDF I have here. I'm going to multiply it by more stuff later to simulate texture colors and such, but this is basically our BRDF at this point, times intensity, which is going to be base light dot intensity. Times, and our last is attenuation, which is our diffuse factor. So, there you go. That is our equation right now. And then I'm just going to return diffuse color. And there you go. That is all there is to our lighting calculation. At least for now. This is going to get a little bit more complicated as time goes on. In case you haven't noticed, this is a rather simple way of calculating light. But as our approximation gets better and we add more stuff in here, this is going to get bigger. But anyways, this is all we need for now. And with that, we can pretty much start going in here and actually using this lighting framework that we set up. However, before we do that, we do have a little bit of a problem here. All of our lighting calculation depends on this vec3 normal, which is essentially the up direction on a given surface. And right now, we don't really have that information. And we really don't have a good way of generating it or calculating it in the fragment shader. And even if we did, I probably wouldn't want to do it there, because the fragment shader is doing enough work as it is. But in order to actually get this normal data, we're going to need to store that in our Vertex. So we're going to need to do a little bit of stuff in our actual code before we move on. So what I'm going to do is I'm going to go into our mesh class, and I'm going to create a new method. It's going to be a private method. So it's going to be private void calc normals. And essentially all it's going to do is it's going to take in the vertex array of data, and I guess I should call it vertices. Okay, I'll call it vertices. It's going to take in all the vertices, and it's going to look at them, and it's going to figure out, hey, this is... Well, actually, I should probably take in... I'll see how it goes. I'll start with the vertex array. So it's gonna, as I was saying, it's gonna take in this vertex array, and from it, it's just gonna look at all the vertices as triangles and calculate which direction is up. So pretty straightforward. And yeah, and come to think of it, I really probably should take in the indices. So I'm gonna take in the int array indices, and yeah. So the way I'm going to do this, I'm going to go in a giant for loop. I is less than indices dot length, and I plus equals 3. So I'm going to count by 3 because I'm going by triangles. I want to look at every individual face. So yeah, I do want the indices. So I'm going to start by getting all the indices for the particular face. So indices 0 is indices sub I. Int I1 is indices sub I plus 1. Int I2 is indices sub I plus 2. So now I have all the indices for the whatever the face is. And yeah. So now I'm actually going to calculate the lines. I'm going to calculate 2 of the lines for whatever face this is. So I'm going to use a vector 3 for that. I'm going to say v1. And that is going to be vertices sub I1 dot get position dot subtract vertices sub I2 dot get position. Wait, actually I'll do that sub vertices dot I0. There we go. And that'll get me the first line. It's essentially going to take a line, say this is the top of the triangle, and these are the corners. It's just going to figure out the line from here to here. It's going to give me a line that's this length and in this direction. And yeah. And I'm going to get one more from here to here. So vector 3f, v2, is vertices sub I2 dot get path dot sub vertices sub I0 dot get position. And now I have a line with misspelling, but that's fine. From here to here. And the way this is going to work, now that I have these 2 lines, is I can calculate the up direction just by doing the cross product between these. Because what do I get if I do a cross product between these? Whatever direction's up from there. So vector 3f normal equals v1 dot cross with v2. And really, that's all there is to it. That gets me the normal. And actually I want to normalize the normal because, well, yeah, I don't want anything funny with this. So, yeah. There's the normal. And, yeah. So, normals of normal length, of course, and yeah, there we go. So, now that we actually have the normal, we're going to want to set all of our vertices to this normal. And here I have a little bit of a problem because I'm going to be storing my normals inside the vertices. But the issue with all that is, well, although I am storing the normals in the vertices, I mean, one individual vertex can be part of more than one face, and this is the normal for every individual face. So in order to make sure this normal is, well, correct for every face, what I'm going to do is I'm going to just I'll do something interesting. I'll put it like that. It'll become more clear as I start coding this. So I'm going to take every individual vertex, and I'm going to set the normal, which is some method I'll add in a bit, to whatever the current normal is. So yeah, this is also stuff I'm going to add to the vertex in a bit. It doesn't have normals right now, but that's okay. Dot get normal, dot add. I'm just going to add whatever normal is I've got. And I'm going to do that for every individual one. Now this is going to make the length horrendously wrong, but that's okay, because the end result will be this will be in the appropriate direction. And that's all I care about. So, because essentially this is just, the direction is going to end up being the average direction of all the normals I add to it. And from there I just need to do one more pass, so int I equals 0, I is less than... Wait, this just needs to go for the vertices, right? yeah, this just needs to go for vertices. So vertices dot length I plus plus vertices sub I equals vertices. Wait, yes, vertices sub I dot get dot set normal to vertices sub I dot get normal. So I'm going to set the normal to whatever the normal is dot normalized, and that will return the direction, or that will set the direction. Wait, no, the direction's already right. What I'm trying to say is this will set the length to 1. So I get the appropriate direction because all of this ends up being averaged, even though it screws up the length. And with the second pass, that normalizes it. So now the length and direction are going to be correct for every single vertex. And this is going to be our algorithm for calculating our normals. Of course, this means we need more data in our vertex because we're storing our normals there. So I'm going to need to change size to 8 because, well, we have new vector 3 here. New vector 3f called normal. And here I'm going to have a new method. I'm going to copy this and use this subpos subtext chord sub new vector 3f 0, 0, 0. It's going to start with no normal. And our correct constructor is going, I guess, our full constructor is going to have a vector 3f for the normal. And this dot normal equals normal. And there. And of course, we just need getters and setters for this. So Alt-Shift-S, generate getters and setters for normal, and generate it at the end, and that's fine. So there. Now that should fix our mesh, except I spelled that wrong. And there. So now we can calculate normals with our mesh. We can generate normals. So now what I'm going to do is I'm going to go into our add vertices method, and I'm going to take our prototype of it. I'm just going to copy because I'm going to change this. And what I'm going to change is I'm going to have a boolean called calc normals. And of course, if that's true, we're going to use our calc normals method to generate normals for our mesh. And yeah, so by default, if we're just passing it in as nothing, then I'm going to do add vertices with vertices, indices, and false. So by default, we're not going to calculate any normals. But if we tell it to calculate the normals, then I'm going to do something. And it's going to be pretty straightforward. So if we calculate the normals, then calc normals, vertices, indices. Ooh, I know. But, yeah. So with that, we have calculated our normals, and then we can just go ahead with mesh generation as usual. The thing now is, we have new data in our vertex. So I don't know why I closed out of it, but yeah. We've increased the size, we have new data, so we're going to need to change a few things. Starting with our util method, because now we're going to need to actually, well, put all our normals in our, in our buffer when we convert it to a buffer. So, I'm going to change this to get normals. Wait, get normal, not normals. So just going to add our normal, and yeah. So now we have our normal data, as well as our position and texture data, in our giant buffer for our vertex. And yeah. So we've got our normals, and now in our our mesh, we're going to want to add this. So I'm going to create a new vertex attribute array for our normals. It's going to be number 2. Okay, so enable that and disable it when we're done. And now I'm going to set it to h2, its size of 3, vertex.size times 4, so same thing as usual there. And for offset, I want to say this plus the size of our, texture coordinates. So our texture coordinates are size, wait a minute, I think I might be doing this backwards. Hang on a second. Okay, so the way I got this number is this is the offset from the starting position. So it's 4 multiplied by the size of, it's 4 for bytes, because there's 4 bytes in a floating point number, times the number I have. This time I have 2 floating point numbers, times 2 for the texture coordinates. So that's 8 plus 12 is 20. Okay, so I'm not doing this backwards. I'm not crazy. There we go. Whew, okay, just want to make sure I wasn't screwing anything up there. And that should put all our data in here. So with that, we finally have all of our mesh data proper. We actually have the mesh data. We can now take this and use this in our shaders. So yeah, let's go ahead and do that now. We can finally implement our lighting calculation properly. And that's about all the time I have for now. So, hope you enjoyed, hope you learned, and I'll see you next time. Now, just in case you were wondering where I've been for these extra 8 days when I was supposed to be off vacation, without spoiling anything, I've been working on something for you guys, and I've been having way too much fun doing so. So, that's about all I can say without spoiling anything, unfortunately, but don't worry, you'll know when it comes. So, thank you, hope you enjoyed, hope you learned, and I'll see you next time.